In this video, I will show you how I built this motor. It's made with very simple materials. All you really need is Legos, a rotor, this, and a magnet hidden under here, as well as a power supply. I'll be using I am using a electric scooter charger for this. I ran this on maximum voltage, 58.8 volts, 2.0 amps. So you can see my power supply, which can take on 60 volts, it's at the maximum, high, run. It's off right now, I had it on before. So first, I will show you how I built the motor by, well, really there's no need to take it apart. In fact, I will just explain to you how I built it. It's easy to build. Under here, however, I will remove this so you can see the magnet I've put under it, just so you know what kind of magnet you generally need to build it. Really, any magnet works as long as it's, well, large and flat, like this one. It's one of those therapy magnets. Except it's without that leather case, so here's just the magnet by itself. It's pretty strong. As you can see, I'm holding the motor, the rotor, down with these. These are just a little housing for the magnet to keep it still. For those of you who don't know how motors work, I will explain to you how a motor works. You see, first I will explain the parts. This, that looks sort of like a crown that's been split into segments, this is the commutator. The commutator acts essentially as a rotary switch. That is what a commutator is for. In fact, commutators from old motors can be reused as rotary switches for, say, LEDs or something, and anything that you can just use it as a rotary switch. You spin it and you use use electric motor brushes or wires. Now normally when it's built into the motor, into the casing, it would have these it would have graphite pads or graphite blocks that are making contact with this. Those are called brushes because they brush against the commutator. They're usually spring-loaded to make sure they always maintain contact because as they spin, you know how graphite wears down over time. So they're going to wear down and they're going to get smaller and smaller. So they have to be spring-loaded to always ensure they maintain contact until there comes a time when they wear away so much there's no brush left and you have to replace it. But this here that I'm holding in my hand is called the armature, aka the rotor. The armature or rotor is the rotating part, hence the name rotor. This over here is the stator. So I've built it out of Lego bricks, as you can see by stacking the Legos and putting them like this. In real motors, it's usually made of metal, though there are some motors, very rare, when it's actually made of plastic. This magnet is a source of a magnetic field, a stationary magnetic field. Now, when the brushes make contact with this, they power a certain coil in this, and that coil turns into an electromagnet. An electromagnet is a magnet that can be turned on and off by electricity, usually just a simple coil of wire. There are many coils of wire. Let's count them, shall we? Where was I? Sorry, I paused the video. Just a little inconvenience. I kind of lost track where I am, so I'll just explain from the last point. So usually it's made of metal in real motors, but here I just made it out of Lego bricks just because it's a model. It's not meant to power anything, it's just meant as a little description. Anyways, each coil acts like an electromagnet when power is applied. So that they generate a field. That field interacts with the magnetic field of the magnet. Usually there's more than one. Usually it's an odd number of rotor coils and an even number of rotor coil, or an odd number of rotor coils and an even number of magnets to prevent something called aligning, which I will explain in a moment. So what happens is that you know how magnets attract and repel because they have two poles. So what happens is that the rotor spins like that. It spins to try to align with the magnet. But oh wait, it can't, because the commutator, acting like a rotary switch, then shifts to the next coil. That coil then tries to align with the magnet, but then the commutator switches to the next coil. And the next one, 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 so on, so on, and so forth. That creates a continuous cycle, which is what keeps the motor spinning. What I just made is called a brushed DC motor. Though obviously that's not the only kind of motor. There are other kinds of motors. There are induction motors, repulsion brushed AC motors, universal motors. There's a lot of different kind of motors. But the brushed DC motor can be seen as the most basic, simple motor of all. It's actually very simple. I will demonstrate it one more time before we end the video. But yes, DC motors are generally used in lots and lots of different applications. I have a ton of DC motors all the way over here. I have this large one, which is from an electric standing desk. As you can see, I've cut a hole into it so you can see all the internal parts. The rotor, commutator, and brushes. The magnets are on either side. It's difficult to see, but there are two magnets. They are in the shape of curves, because that's the most efficient, strongest magnet. I also have this, which is part of a little fan over here and here. This is also a brushed DC motor, except it's complete, like this one. This is see those magnets? They're curved. That's to make it more efficient. And this is part of a DC motor from a Snap Circuits kit. Though unfortunately it is damaged. I don't have the end cap. The end cap is what? The end cap, also known as commutator cap, is this. It holds the brushes. It holds the brushes and ensures the motor is able to spin. Usually there is a bearing or bushing located over here which supports the shaft. The shaft? Usually the shaft on the rear of the motor, this is where stuff like pulleys, drive belts, or gears can be attached, so the motor can be put to use. The motor over there, unfortunately, I don't believe there could be much of a use for it other than for educational activities. Because since it's held with Legos, trying to put a load on it would probably just end up destroying the thing. The rotor could, Lego bricks could separate. You know, it's just not good. It's more of a educational. This over here is also a DC motor, a toy motor, specifically an FS130 or FF130. 3 volt, 12 volt, generally in the range of 3 volt, 6 volt. This is also a DC motor. Inside, you can see the rotor through this little hole. It's hard to see, but if we zoom in, there it is inside. Now, back to our motor. It is very simple, as you can see, and I will demonstrate it one more time before we end the video. Like I said, here we have our little setup. I'm just putting the phone in a container to help keep it steady. To help keep it steady, even though it's not the correct way. Here we get a good view of the motor. As you can see, it spins very... Oh, that reminds me. I forgot to explain. Yeah. These over here on either end, it has bearings. They don't, usually the cheaper motors have bushings in them because the bushings are simpler to manufacture. They're not expensive, they're cheap. Because there is in fact practically no moving parts except for the shaft that goes into the bushing. But these just have simple ball bearings. Now we will demonstrate the motor on different voltages. And the lowest voltage, which this power supply is 3 volts, to the highest, 58.8 volts. Here it is on 3 volts. As you can see, it doesn't spin very fast because the voltage is too low. If I give it a little push, it still doesn't really spin. But if we raise the voltage just a bit, it spins a little more with very limited arcing. Normally, the brushes are usually made out of graphite, but in this case, I just have them made out of wires. Though it is very inefficient, the wires get hot. Here it is on slightly higher voltage. More pronounced arcing. And here it is on full voltage. Notice how it spins much faster. That's another interesting thing about these motors. The higher the voltage, the stronger the magnetic field generated at the coils, and the faster it'll try to align. So the cycle goes on faster and faster and faster. However, there is one thing. You can't overvolt the motor. You can't give the motor too much voltage because they're not meant to handle that, and I will demonstrate that with one of the small motors. You will see what happens. Scientific purposes only, we will explore what happens to a motor when it is overvolted. Starting at 3 volts and going all the way to 58 volts. You will see just how destructive overvoltage is for a DC motor. Here it is, voltage on. Did you see that? That, my friend, is the power of overvoltage on DC motors. Always be extremely careful on your DC motors, ensuring that you're using the correct voltage. Undervoltage can also be equally as dangerous for motors, especially large motors, because the motor, catching my breath, will draw lots and lots of current. Excessive current, which will overheat it. So always ensure that you run the motor at its voltage specifications and don't stray too far above or below the voltage. Most motors, well, the small motors, for example, 12-volt motors can usually go double their voltage. For example, RC300 motors, RC370 motors, for example, if it's 12-volt, can maybe handle 24 volts, not much deal, but now we will open the motor